Greetings, gentle readers, fellow earthlings. Today would be March 3, 2026. And in reading foundations today, they'll be about reading and foundations. Reading is a great exercise and experiment of the entry of an individual into the world of text, the world of reading, the world of words, and that it's a wider world, a deeper world, a richer world than the usual accoutrement of images worth about 1,000 words, if that. And while that's so, then another great wider setting of experiment to the senses is the sky survey. So the notions of the planets and their alignment and eclipses and syzygies and other aspects of when the stars align, as it were, has that this is a great observational setting, an observatory of the experimental setting of the sky survey. So there was a lunar eclipse, a full lunar eclipse. This morning about 3 o'clock or so. I set my alarm to get up and see it, and lucked out that it was over the river there, over the hill, and at that time of the nighttime. And I've seen lunar eclipses before and a solar eclipse or two. And so I already was familiar with the experience of watching the development of the shadow and the light and the shading and the image that results from it, about that the aspects of the dynamics, and here's discussed as like large Fresnel lensing and the occultation or the obstruction lensing vis-a-vis the focus of usual optical lenses, as they're called, lensing and optics, that then the account in the wider setting where the image of the moon's face spins around and these kinds of things is perfectly natural and quite well explained by a theory of light after something like the Arago spot in the occultation setting, when, for example, a light emerges from behind even a small occultation or obstacle, that obstruction, that it brings the image of the light source around. Then this is readily apparent to anybody who can find that, is this superclassical behavior of the special character of optical and visible light, that optical light is special, then has that it's events like those in the extraterrestrial, yet more so the macro scale, that help to show that since millennia, these kinds of experiments were able to show not just the usual ideas of like camera obscura, pinhole cameras, and the like, or as for Arago spot, Arago or Arago spot. And the fact that it's there, it's a little dot in the middle of the shadow of a light behind a globe or something like that. That then the actual effect of the imaging is spinning around, and the limning, the lining of the image with the light is sort of these reverse optics in a sense, and so the optics are good. Is the idea here, and that many things that science in the theory today still calls aberration, optical aberration, like coma and these sorts of ideas, or lens flare and these kinds of things, which are just tacked on to make renderings and stuff like that. It doesn't quite look right without it. But it doesn't really say the science and the theory why it does it. But the optics must be good, That this makes for these sorts of accounts why it's a greater than world of reading in the text that makes her so, why that can be explained. And then it gets into the pure application of the mental faculties for the superclassical aspects of the theory. Why then to make for something like the L principle, that light speed is a constant, and you can read from the physics today and Logos 2000 all these comments about that from all these reasoners, all the latest greatest AI, And whether or not you think that AI thinks is kind of so that inference is as inference does, demonstrably the thinking, and the demonstrated command of concepts and the contemplation and deliberation thereof. That it's gratifying then that a theory can supplement the usual classical theories with these super classical accounts, so the potentialistic accounts, those being real, and that also it gives for in these effects, like similarly for the optics, then for kinetics and kinematics, there'd be the Allais effect, Allais, the Allais effect, which for paraconical pendulums in a syzygy or eclipse, they make a flip. And these, which is not explained by the usual theory, that they do, and it's fine, and it's real, and anybody can see that. It might not be so often obviously visible from cameras and stuff, and also about the reflection of the Earth's image on the moon during the lunar eclipse. There's a number of things going on when the stars align that makes for a usual kind of a what's considered relevant part of foundations, because it's the theory of everything, and so that's what it is. Large Fresnel, or Fresnel, Fresnel, one of the great opticians of all time in science. Fresnel is considered part of these F-Lorentzians. E for energy, and then kind of like about Einstein as having combined some of these other aspects to like sit carefully in the middle without saying much, don't rock the boat, vis-a-vis F-Lorentzians. The Lorentzian defining the notion of a metric, that the three space terms, the sum of their second partials, plus or minus, that minus plus or minus the time term, its second partial differential, or up to first order, and these kinds of things, about under the quadratic for Cauchy-Schwarz, and this so limited in that kind of sense, equaling this ds squared, the metric, what that's supposed to be, the measure of length, and the norm is supposed to be the measure of distance. These F-Lorentzians for Fresnel and Fizeau said, for example, that Einstein's great account just kind of took the half of Fresnel and half of Fizeau and put them together, and then got about a quarter of those, and called that a corner, and it's good, which it is. Then these other accounts like Finlay-Freundlich and FitzGerald, who's the kind of the giant about space contraction, and Finlay-Freundlich about gravitational things more often, kind of like Fresnel and Fizeau go together about light and light speed, and whether light is optical or linear, and then FitzGerald and Finlay-Freundlich or Erwin-Freundlich go together kind of about gravity. And then Feynman is kind of about virtual photons, those being kind of the non-explanations that begin under some various theories of the subatomic, which is kind of already a contradiction in terms. That then these other accounts of these F-Lorentzians for the fields and forces, but conveniently by the names of all physicists from the last few hundred years whose developments are considered primary and fundamental. Then their deconstructive accounts make for all these, their Lorentzians are set up and satisfied. So then this account for light, and then light speed as a constant, is then for another aspect of about there's no absolute motion, that there's that there is. The ether theory always kind of comes back as like, that's just kind of a complementary concept to relativity theory. Anything that's framed in relativity theory coming together can be framed in ether theory kind of going apart. But it's not so simple always to paint the corners of that sort of account. But they exist, of course, like Dedonder and Dedonder about an integral setting for gravity, and the gravific, even better, a potentialistic account the same. Make it so that then superclassical sorts of accounts are made from deconstructive accounts, as what's resulted are severe abstraction, a mechanical reduction or electrical reduction. The usual account, therefore, sort of both sides of Lagrange, that on the one hand he's got like setting up for the Hamiltonian, a bit of continuum mechanics before and after, a prior sort of count that makes for then the balance of forces as of real and potential forces. That the potential forces are half of Lagrange's account. That the other half of Lagrange's account, or Lagrange's other account, is the outside of that. And so there's something to be said that science's course of the severe abstraction of the mechanical reduction, or reductionism, has that it's arrived at today. There's again kind of rekindled a great debate about the reductionism versus realism, because reductionism is essentially just kind of like, this is the least attachment. Well, we're not exactly wrong. And it's of great importance to be able to predict things, if that's a term to be said, that to predict what the theory would say, at least. According to science, never predicts anything. It's just not falsified in this sense. And theories aren't confirmed; they just aren't not confirmed. That's the only true. That's the only conscientious account of science. But you can still predict what the theory would say mathematically, because mathematics can be deterministic. That the severe abstraction and the reductionism has seen that because every other year an account of a Nobel Prize in physics gives one of them to reductionism and the other to anti-reductionism, that realism has to include all the data and not just like 2 out of 3 on a good day when the timing is right and hoping the optics are good. That the fuller sort of account is an anti-reductionism, but that just being expansion, and then that being realism. So here that's then part of many usual accounts of why that fits naturally in the language of science and the history of science and the mathematics underneath it, which it is. And so that thusly, instead of just trying to tack more stuff on top, which is doomed to topple on over, that it's a fuller, more robust way to make for a fair and thorough and fulfilling account of foundations. Well, then I'd like to get through the rest of this box of books, because there are many others, and so I'm just going to kind of clip through these at a pace. This first few, I just got these at a bookstore. I happened to be driving across the state and getting some stuff, and then I went to this bookstore, and it was a great little bookstore. And I look forward to the next time to go back, because I found a bunch of stuff. A Dover reprint, Terrell L. Hills, Thermodynamics of Small Systems, parts 1 and 2. So as regards to thermodynamics, we got first and second thermal law. After Boyle's law and this sort of account, then there's Kelvin, and for the second thermal law. And for Boltzmann, the other day a discussion came up about Boltzmann constant. It was like, well, did you know that Boltzmann constant is got in it mostly the molar gas constant everywhere? But that's really just kind of another root of x squared plus minus x plus minus 1. Just like phi, the golden ratio, it's just another one of these roots. And so that this constant, which is like 8 point something, vis-a-vis Boltzmann constant is like 13 point something. And then in all the units, is not a physical constant itself, it's a mathematical constant. So somewhere along the lines from Hooke's law, Clapeyron, Arrhenius, Kelvin, Rayleigh-Jeans, and Planck, that's it's kind of lost which one of those where those would have why it makes for an account of why it's just not so that Boltzmann constant is thoroughly a physical constant. And even when it's just given as derived from other fundamental physical constants, that the System International of Units has seen one of the most severe accounts of the severe abstraction and the reduction, because it's like if all I'm guaranteeing is first order approximation, I'm willing to let everything else go as long as I got less constants. The Boltzmann constant is everywhere in thermodynamics and all the statistical mechanics involved with thermodynamics. Second law particularly, and that defining entropy for everybody. Not that there isn't another definition, because there is. And then that defining information for lots of people, which is kind of some information. It's not like all the information. These are the kinds of accounts. So thermodynamics of small systems, then, one would imagine would be a particular specialization about first and second law with regards to molecular systems, usually. 1964, published in the United Kingdom. Dover reprint, 1994. Environmental variables, mu, v, and t. So speaking to the PV equals nRT and the ideal gas law. Statistical mechanical digression, other environments, general treatment of environments, environmental variables, environment NP and T, environmental variables N and T, environmental variables N1 through NC, P and T, chemical and phase equilibria. And so what he's done for the mechanical reduction is he's broken this out to these differences to considerations and concerns of the setting of a gas model and a pressure model associated with a gas model, the compressible. And so it's already, it can be noted and read off when it's already understood that there are deconstructive accounts of otherwise these ideal formulas, that they're each according algebraically, these various implicits, that the author has a breakout of these for various reasons. Binary Bragg-Williams crystallite, dilute and ideal solutions, dilute gas of small systems, invariable pressure, incompressible small system, thermodynamic relations, applications of theoretical models, solvent effects. These are being sections within the chapters. Chemical and phase equilibria. Environmental variables mu, v, and t again. And a reprint of Thermodynamics of Small Systems by Terrell L. Hill, Journal of Chemistry and Physics, or JChemPhys, 1962. Introduction. In ordinary thermodynamics, thermodynamic functions are defined and mathematical interrelations between these functions are derived from macroscopic, strictly infinite systems only. Our main object in this book is to extend the range of validity of those definitions and interrelations to include small non-macroscopic systems, e.g. a single macromolecule or colloidal particle. Let us turn immediately to a simple illustration. Suppose a certain one-component macroscopic solid has a Gibbs free energy. With regards to free energy and potentials and the ionization and the liberation of energy, and then that be always considered to kind of naturally go to heat and entropy in the kinetic and kinematic. In the chemical, with regards to the ionization potentials, that being the electrical, here that's the thermodynamics account is the content is the Gibbs free energy. F equals NFPT, where N equals number of molecules and F is a function of P and T only, and they give some solutions that fall out of that as according to their partials under the terms. Give some inverses, basically showing the approximations or on the order of the relations vis-a-vis approximations and given orders associated. And here, with regards to just for addition formula, these subtraction formula, it just results in terms. And it's like, well, here's this term in two of these variables out of three, and so here's how the other one would be minus that, taking the partial, because that's just kind of like dividing it out. And so then that just results that later they could just, in these approximations, they would be having formulas that just have that cancel using the most direct tool of mathematical physics, high school algebra. So. Now consider a colloidal particle of the same solid, small enough that correction terms must be added to F. The free energy. Correction terms, interacting terms, correction terms, this and that. So I'm gonna carry on from here, because this then is for a close reading after already having something like the theory of thermodynamics and all that kind of stuff, and for a lot of different kinds of accounts and approaches. And so later on in the book, he's got various conjugates and symbols: box, double cross, tildes, bar, over bar, and these kinds of accounts in otherwise those same terms just mentioned. So they're just kind of carried on throughout all these different kinds of blocks, the switches of the blocks, these kinds of things. So I suppose that then, as in getting the next book, then I'll mention what I was thinking about mentioning about the last talk. So it's about individuals and infinite integers. So there's the laws of numbers, laws of large numbers. And so the usual idea of an account of infinity is like, well, unless it's infinite, it's not infinite. But if it's sufficiently large, we can't count that high. So there's the actual infinite, and then the not actual infinite, usually called the potential infinite, meaning it's unbounded. And the treatments for delta epsilonics and the usual linear curriculum for the introduction of precalculus and calculus is the unbounded and the potential infinity, the end. But it gives kind of it gives an inductive account of the definition of limit after attaching that to the geometric series for a real analytical character, mensuration, the measuring of things, the integral analysis. That the account of this formalization, the formalisms, and the derivations has that the potential infinity is usual, and it's kind of transparent to an inductive account. So then the actual infinity is different. It's actual, it's real, it's natural, it's infinite, it's not finite. Then whether it includes infinitely grand members for the infinitely many members it contains, the Archimedean vis-a-vis non-Archimedean account, super Archimedean, has here that that's part of the laws, plural, of large numbers, because the usual law of large numbers is just the law of small numbers, that it's unbounded. But the actual law of large numbers has things, for example, that it's like there's actual infinites in it. Or that there's not a standard model of integers, there's always an extraordinary one for completing the limit, that the limit is a sum, and the sum is the limit, making that true instead of defined. So between the potential and the actual infinite are accounts of the practical and the effective infinite. And so that's just kind of reifying that it's like, well, it's not infinite, but it's big enough that it's going to work out for my means of approximation to not be any different. That's finite element analysis. And whether that's smaller than potential infinity and the unbounded has that, yeah, it is. But it kind of sits between potential infinity, because the concept there is just like, I got a law of small numbers, that's a law of large numbers. And then anything greater than that. And so when it's practically infinite, it's like, and there's also enough. There's the extra bit of that. And then the effective infinite is making that it's like, and furthermore, there's no way I can overcome that. It's unbounded, and there's for the idea that there's a law of small numbers that kind of what's so for a number, as if there's a number larger than it, is like there's a number arbitrarily larger than that, while still all Archimedean and finite. And so an actual infinite would be a practical and effective infinite to the potential infinite, and the potential infinite would be less than a practical and effective infinite to the actual infinite. So that was just part of these ideas of the individuals in infinite integers, because there are at least three laws of large numbers, three kinds of Cantor spaces, three models of continuous domains, three probability limit theorems up front, and these sorts of accounts, why mathematics has these. And then putting that in primary and central in foundations is a part of the research and study in foundations. For real analytical character. For the real valued, i.e. part of the, like having a value somewhere between 0 and infinity, exactly 1, where those values are trichotomous and ordered. Analytical, meaning it's sensible and fungible and tractable, how we can arrive at that number from other numbers and their systems and derivations. Character, meaning a number. Again. So. Fetter and Waleka's Nonlinear Mechanics, a supplement to theoretical mechanics of particles and continua. Stanford and William and Mary. A supplement to theoretical mechanics of particles and continue. Dover reprints. Other Dover books of interest, here it says. Includes like Bohm and Einstein and Fermi, Mazur. That's this non-equilibrium thermodynamics with de Groot and Mazur. That'd be interesting, I suppose. Quantum field theory and the fundamental problems of physics. J.K. Curry, Weinberg, and Witten. So, Feder and Wallecka here have this nonlinear mechanics. And what I expect it to be about is these things above the second and third order that start to show up from after gyroscopic terms. And then besides nonlinear oscillations, like there's the great account of a book called Nonlinear Oscillations, which is the world's first catalog of these put together for nonlinear oscillations that result having periodic repetition. Then this nonlinear mechanics is kind of the idea of what happens when something topples, or the gyroscope falls down, or the gyroscope holds up. These third order and beyond effects to the thing. So the authors have in 2005, when Dover Publications agreed to reprint our textbook, we decided to write a short additional volume on nonlinear mechanics that would include material that each of us has used in recent graduate classes. Some of them focus on various aspects of nonlinear phenomena in both fluids and discrete systems of particles. We start with the onset of hydrodynamic instabilities, particularly the Rayleigh-Benard convective instability in a fluid heated from below. The associated nonlinear Lorentz equations provide a simple model for the chaotic behavior far beyond the onset of convection. We then study the logistic map, which illustrates period doubling as a different route to chaotic dynamics. So the logistic map is a very usual thing found in predator-prey models, and otherwise models with feedback. And so the different integro and the integro differ have that the integro differ and the different integro, and here's about Duhamel principle, adding always a non-zero term one way or the other, that this rising or falling term. Duhamel principle about integro differ and different integro, just like having an addition and multiplication, together with zero in the middle, that is non-zero in these usual accounts of systems with any kind of feedback at all. So, for example, about then many different accounts and anything to do with the non-adiabatic. These are things then about like particulars in the experimental setting, notable to be set up with kind of simple things like this alembic is spherical on the bottom, and this Bunsen burner is very metered. And so then these are kinds of things that be controlled in the configuration and energy of experiment, and then worked up into with these mathematical treatments that are the only way to give what's correct, because they involve dynamics of other systems, which under first and second order approximations and their applicability. Nonlinear continuous systems, discrete dynamical systems, and there's much I'd like to read from this and kind of scan through this. Here, for example, it comes up with on page 12 in item 1 here is KH is greater, using not just the greater than sign from arithmetic inequality, but two of those stacked together, meaning much greater. Illustrating this not just a matter of like, according to a small difference, the difference will be small, but when there's a large difference, there'll be a difference at all. And so this helps to show that then otherwise this is about terms and conditions, just establishing that it's like, yeah, for a law of small numbers, there's a law of large numbers besides. And then there are at least 3 of those is its own sort of count. So that's built into this. Otherwise, why this would not be necessary. Sums and products of partial differential terms, some volumetric, some areal, on phi or phi, that generally extending out for f for function, usual accounts of a functional system, say. G of a difference times sigma of tau, usually time, and del or nabla squared, or the Laplacian often enough, or the Poisson. These kinds of things. So high school algebra in a mathematics degree with engineering. These sorts of things. The transverse part, the Laplacian here, not the Poisson. So. Rayleigh number, another qualitative quantity. Duffing oscillator. Lorentz equations. Often set up for continuity systems, continuity equations. Liouville's theorem. The reader may indeed feel that we have spent an inordinate amount of time on Liouville's theorem. So Sturm Liouville come up with like the existence uniqueness of linear solutions to linear systems of linear PDEs. As justification, we recall that this result was one of the cornerstones of classical statistical mechanics, so that a clear understanding is important. Note that the Lorentz equations, which are not a Hamiltonian system, illustrate another possible situation, namely the continuous shrinking of the phase volume. With regards to the Hamiltonian, the other day here, there was leafed through a little bit of Ruth's, R-O-U-T-H's, tome on fluid mechanics. So the Routhian is actually set up as like, it sits next to like the Hamiltonian with the Jacobian. And that being these matrix forms that make for systems solvable. And that the Hamiltonian is used pretty much everywhere, because then after the Gaussian account of singular vector decomposition, or SVD, or these kinds of things, and rank echelon reduction, finding solutions to systems of equations as modeled by matrices, and superposition being built out of that for finding roots and the solutions in terms of expressions that can be eliminated by deduction about each other. That being is like that's what it is, you know. That's why it is the Hamiltonian. And then for eigen systems and this kind of stuff is like, and then we'll make it kind of triangular. It's in a corner, so let's turn it into also a corner, and then we can get out whether the determinant is non-zero and singular, and so some of these products of the transposes or the adjoints fall out, cancel algebraically. You know, authors here are pointing out that it's like it's in the middle of Liouville, so you're gonna have to figure out this other stuff to do with it as well. The authors write Hamiltonian with a lowercase. So usually, like when writing the Lagrangian or something like that, it'll be like uppercase, the proper name. Lorentzians, and this kind of thing. But Euclidean, for example, or Archimedean, or sometimes Abelian, but not so much. Commutative groups, but the Archimedean and the Euclidean, and these sorts of accounts have a lowercase name. It's entered the language of that the aspects of it are so. The authors here have that for Hamiltonian, in a sense, but not Liouville. Mentions about Hamilton-Jacobi equation. A very rigorous setting for making things fungible and then tractable for systems of linear equations. Degrees of freedom, schematics, and getting into the cases, linear and rotational. Setting up topologically equivalent to a two-torus. Getting into issues of the fundamentals and other matters of geometry and the algebraic geometry, then to make for why these things can give up and down. Substitution of the expansion in equations 14.17 and equation 14.18 then gives the new Hamiltonian. And then the footnote says the quantity f of J1, J2 can again be evaluated at resonance because it enters multiplied by epsilon. So this is the It kind of speaks to the comment in the introduction about the logistic and the doubling of the period and the resonance with regards to that being the exponential, and then also about that being about halving and doubling these sorts of accounts. Resonant disruption of phase space. So part of the grab bag toolkit, it's a tool of methods in dynamical modeling or differential or integral analysis together. Mikhailov and Ojeshik's, MD Mikhailov or Mikhailov and MN Ojeshik or Ojeshik, unified analysis and solutions of heat and mass diffusion. So again, about the thermodynamics, and then about unified analysis, kind of taking it's more than like a fundamental elementary approach kind of a thing. By its word, that's what it would mean. And then some different in these Dover classics. Then they got like Max Born, Max Planck, Erwin Schrödinger, Degas, physicists. Lanchos, a mathematician, linear. Carl Boyer, the history of the calculus and its conceptual development, pointing to many important examples since Cavalieri and since Zeno of things that are relevant about the mensuration again, about how many points are in a line and what does it mean for an ant to walk its trail and how many feet is that? These kinds of things. Unified analysis and solutions of heat and mass diffusion. A vast amount of work at almost any level of mathematical and physical complexity and sophistication is available in the literature on the subject of heat and mass diffusion. In recent years, with the availability of large-capacity, high-speed digital computers and improved numerical schemes, significant advances have been made towards the solution to the more complicated types of these problems by purely numerical finite difference or finite element means. Despite such advances in numerical solution techniques, however, there still exists a vast class of problems of practical importance that can be studied by analytical approaches. Furthermore, analytical solutions, when available, are advantageous and they provide a good insight into the significance of various system parameters affecting the transport phenomena, as well as accurate benchmarks for the numerical approach. Therefore, literature on the analytical treatment of heat and mass diffusion problems is still growing, and the number of types of problems to be solved remains large because of the varied combinations of physical parameters that govern conservation equations, or continuity equations here, the boundary conditions, and the couplings between them. Forces and couplings, stress and strain and shear, the usual counts of tensors, almost always written as Hamiltonians for the linear sorts of accounts, and then just left for the nonlinear and the singular solutions is its own body of work altogether. Because it takes 15 years of school to compute your first Hamiltonian, say. Now, you can obviously take a much abbreviated course and get to it quite more directly, but it's expected when you're learning stuff that you kind of get a universal education along the way. Let's see, chapters, 14 chapters. Basic relations, the general solutions to 7 different classes of heat and mass diffusion problems, eigenvalue problems, one-dimensional problems, Class 1 solutions apply to steady-state diffusion, Class 1 solutions apply to heat flow through fins, Class 1 solutions apply to time-dependent heat and mass diffusion, Class 1 solutions apply to force convection in conduits, Class 2 solutions apply to heat diffusion in one-dimensional composite media, Class 3 solutions apply to heat and mass transfer in capillary porous body and heat transfer in entrance concurrent flow, Class 4 solutions apply to heat or mass diffusion in one-dimensional heterogeneous media. Class 5 solutions apply to mass diffusion in chemically reacting systems. Class 6 solutions apply to heat, mass diffusion, and developing duct flow. Chapter 14. Then Class 7 solutions apply to diffusion with chemical reaction. So that's out of the Chapter 2, the general solutions of 7 different classes of heat and mass diffusion problems. So for a program that's kind of like it's a switch block, and it leads to combinatorial complexity and combinatorial explosion. And kind of like the potential, practical, effective, and actual infinity is just a switch block. It's qualitative. Let's see. Will this be gotten through? No, not. This is one of the best books that I had for a while. For a while, I thought this was one of the best books. Ahmed Ashabana's Dynamics of Multibody Systems. So this speaks a lot to the difference between kinetics and kinematics. It's dynamics. And so for a while, and as I've learned, there are other key influences that would go into these kinds of accounts. For example, the general treatments of kinematics, which are generally as like we take some gears and we put them on a plane, or we're trying to drive a steam locomotive any possible way. You know, the dynamics of multi-body systems gets beyond gears and kinetics and pendulums and levers and the like, machines to complex machines. Then for the dynamics of multi-body systems, this is a great book, and it's from Cambridge University Press by Ahmad Shabana, University of Illinois at Chicago, 1998. Multi-body systems, reference frames, particle mechanics, rigid body mechanics, deformable bodies, constrained motion, computer formulation, and coordinate selection, objectives and scope of this book. Talking about reference kinematics, the rotation matrix. So these are the tools. Properties of the rotation matrix, Rodriguez parameters, Euler angles, direction cosines. Now the direction cosines speaks a lot to the director cosines, direction or director cosines, speaks a lot to the integral analysis, because it's encountered there kind of in the beginning of that with regards to then the solutions of integral equations, then trying to relate that to that this is kind of about in reference kinematics, then that would be it's the same kind of idea. Relationship between different orientation coordinates. And then 5 or 6 more chapters, analytical techniques, generalized coordinates, mechanics of deformable bodies, so stress and strain relations, equations of equilibrium among those, constitutive equations, the viscoelastic, the deformable. And I mean, something that gets deformed can be deformed back to the way it was, or whether that is or isn't so. The malleability and ductility, for example, or just a bubble, its volume. Floating frame of reference formulation, finite element formulation, or as some way to get solutions. The large deformation problem, linear algebra. The virtual work of the external forces. That is the generalized forces. So this is kind of set up towards to lean back into an account of the integral analysis, the integral formalisms. I don't know if it's kind of written right in here like that, but these are differential equations, but they'd be connected to integral equations to give the solutions of otherwise singular or recurrent systems. These kinds of things. But this is a great work, and I feel much more familiar with it now since I haven't read it in a decade or two. Introduction to Solid State Physics. Kittel, Kittel. Kittel, Wiley. This was a library book. They retired it, so I hired it. Charles Kittel, Professor of Physics, UC Berkeley, 2nd edition, 1953 and 1956. Brought about largely through the application of quantum mechanics, kinetic theory, and the theory of defect structures. So the defect is like where cracks begin, or it's otherwise how and why it would be figured out that if something's going to break, or if it's something's going to have a kind of a wavelet in the model of waves, that it's otherwise when and whether to introduce that as like an impulse, that it also gets in other motions of the stochastic or the random, vis-a-vis stoichiometric or the elementary, these sorts of things. Materials. Solid-state physics and modern chemistry to investigate, develop, and apply metals, ceramics, glass, semiconductors, and polymers. In addition, but perhaps less obviously, research in atomic energy and electronics has catalyzed advances in the technology of these same materials. The general plan of this series of books is to present the science and technology underlying the behavior and the manufacture and the technical use of all important solid materials. Serious overlapping will be avoided by having available to all authors the current state of development of the whole series so that each book can be better integrated with others related to it. Holloman. Hollomon. Holloman. This volume is intended as an introductory textbook in solid-state physics for students of physics, chemistry, and engineering. A course in quantum mechanics is not prerequisite in understanding most of the book, but the reader should be familiar with the Planck radiation law, the de Broglie relation, the Bohr theory of the hydrogen atom, the Zeeman effect, and the wave equation for free particles. So then we might also talk about the Faraday effect, the Bohr theory, and then nucleons theory, or the nucleonics, de Broglie and Bohm, and then as for Planck radiation, that's something is related, like in the discussion here about the Boltzmann constant being talked about before, and physical constants, when they're really mathematical constants, do their derivations. So the radiation, and it's radiation again, just kind of figuring out whether it's quite a classical account again of radiation, or Huygens principle, for example. Solid-state physics. Several advanced topics requiring a formal background of quantum mechanics are developed in appendices. So some of the things it would require knowledge of the formal account, like having gone to school and sat it in physics class, because the formal account is given in like physics 301 or something like that, quantum mechanics. Then knowing the mathematics about that too, then kind of makes that all clear what's gone into it when it comes out, compared to like the algebra, the expression, the equation, the formula that comes out. So yeah, because otherwise it could be, and otherwise that's how it would be talked about specifically enough to connect it in other algebraic derivations that can be written out and relayed. So then it just results in symbolary and a formulary of this stuff to make it predict the theory that it would be mathematically. Gaussian CGS units, so not SI units, but particulars, are used except where otherwise noted. And that there are CGS units that are not Gaussian. Description of crystal structures, diffraction of X-rays by crystals, classification of solids, lattice energy of ionic crystals, elastic constants of crystals. So a lot to do with semiconductors, and as well with regards to X-rays and these sorts of things. Lattice vibrations, thermal properties of solids, dielectric properties, ferroelectric crystals, diamagnetism and paramagnetism. Among the kinds of those, the antis of those, ferromagnetism, its own kind of particular account, and all these kinds of things that go on with it. Free lecture model of metals, band theory of solids, Brillouin zones. It's another thing where the like with the Hunt and Bauer processes and stuff in Brillouin zones, that's from the nonlinear accounts and the non-standard accounts these days. It's how those things are talked about. It talks about like things like Hall effect, consequences of the effective mass, Brillouin zones, wave functions for zero wave vector. It's kind of like a monopole. It's like, well, how can we talk about something with zero? Because 0 meters per second is infinity seconds per meter. It's like, yeah. Actual infinity. Ferromagnetism and anti-ferromagnetism. Superconductivity. The Bloch theorem, the London equations. So that's what I'd like to look at here, the London equations about Fritz London. I was looking. I have a book somewhere that's kind of got Fritz London more included in of him. But then here I'll just look and see what that is. 451 after the Bloch theorem, thermodynamics of the superconducting transition, and then the London equations, then superconductivity at high frequencies. So this book has been around for 80 years, almost 60 years, 70 years. That anybody could have spent the last 50 years kind of just going over about 5 pages of this book. The Bloch wall. So the Bloch wall reminds me of the cube wall. So the term Bloch wall denotes the transition layer which separates adjacent domains magnetized in different directions. The essential idea of the Bloch wall is, and so you usually hear that as B-L-O-C-K, block, like a wall made of blocks. This is B-L-O-C-K, somebody's name. Bloch wall is that the entire change in spin direction between domains magnetized in different directions does not occur in one discontinuous jump across a single atomic plane. Rather, change of direction will take place in a gradual way over many atomic planes. So this is super classical because basically it would have to spin around like infinity times in a second. So getting into notions of spin and this kind of stuff. The reason for the gradual nature of the change is the fact that for a given total change of spin direction, the exchange energy is lower when the change is distributed over many spins than when the change occurs abruptly. So relating this to matters of wave and particle mechanics, but it's a continuous process. And here is like kind of like, you know, light's supposed to be quantized, but light's frequency is infinitely variable. And so here it's just giving an account of like this Bloch wall is an account of like, because otherwise to get up into the superconductivity, and it's like, what does that mean? It's like, well, remember when this is a constant, so in all our algebraic formulas, it's like resistance or something like that. So it's always a finite number greater than 0. Well, what happens when it's 0 is what we're talking about. Because then you'd be dividing by 0. And that's what superconductivity is. So Bloch wall, 451, 431, 441. Superconductivity. So the previous chapters like Stoner, magnetism and matter, Methuen, Bates, modern magnetism, Kittel. Here, this is Kittel, I think. Physical theory of ferromagnetic domains, magnetism. So this has been irrelevant, all kind of stuff like magnetic cores and memory and stuff. Chapter 16, superconductivity. Superconductivity was discovered in 1911 when Kamerlingh Onnes, O-N-N-E-S, observed at Leiden that the resistivity of mercury vanished completely below 4.2 kelvins, the transition from normal conductivity occurring over a very narrow range of temperature of the order of 0.05 kelvins. Persistent currents. A ring of superconducting material is cooled in, and so this gives consequences that also happen to match up according to the model when resistance equals 0. The Silsby hypothesis. Silsby, 1916, suggested the important factor causing the transition back to the normal state was the magnetic field associated with the current rather than the value of the current itself. So the spiral wave and wave spirals are in effect here. Meissner and Oeschenfeld. So Meissner is kind of well known for the Meissnerizing, being able to put something in a magnetic field, make it like levitate or otherwise act as an invisible sort of body, according to otherwise magnetic fields and this kind of thing. Meissner and Oeschenfeld, M-E-I-S-S-N-E-R, and Oeschenfeld, O-C-H-S-E-N-F-E-L-D, or O-C-H-S-E-N-F-E-L-D, Oxenfeld, showed that if a long superconductor is cooled in a longitudinal magnetic field from above the transition temperature, the lines of induction are pushed out at the transition. So that's that the existence of that is where it's transparent, is kind of as mentioned. Intermediate state. And the Debye temperature. So you usually hear about the Debye length. The experimental results, these are the very suggestive relation that temperature T sub C over theta, big theta equals a constant, where theta is the Debye temperature, that theta is proportional to the sound velocity v, which is termed proportional to root m. Constancy of Tc over theta implies that lattice vibrations have an important bearing on superconductivity. It's a clear-guided theory by suggesting that electron lattice interactions must be taken into account. So cavity resonators everywhere, usual sorts of accounts, make what Y Casimir and this kind of stuff. Non-ideal superconductors. Lassarew and Galkin, Lasarew and Galkin, Galkin, has shown that all the characteristic features of a superconductive alloy can be reproduced in a chemically pure specimen of a nominally ideal or soft superconductor by application of a severe inhomogeneous strain. They found that for tin on going from the unstrained to the strained condition, Tc in temperature conductivity increased from 3.72 degrees to 9.0 kelvins, while Hc at 2.0 K increased from 210 to 15,000 Oersteds, the field. E cross B, D cross H. Yeah. These kinds of counts. Superconductivity. Daunt and Mendelssohn. Holm, Mendelssohn, and Olson. Holm. There is at present no quantum theory of superconductivity, which is generally accepted, although the work by Froelich and Bardeen gives the impression that a period of progress may be close at hand. We first discussed several theoretical topics, including the London equations, which help define the problem requiring a solution. I'm going to just look at this a little bit more later while I kind of skim through some more of these books, as I'd like to put this box with. Well, this is a big book. This is Israel Ashley's Intermolecular and Surface Forces. And so, yeah, this box is going to get gone over a bit more, because this is about, like, you know how everything's atoms and particles and be kind of grainy? Well, what happens when it's just kind of smooth? It's the surface. So I'm going to look at this some more in next time, maybe tomorrow. Mathematics of Classical and Quantum Physics by Byron and Fuller. So this is a very well-known sort of textbook. This book is designed as a companion to the graduate level physics texts on classical mechanics, electricity, magnetism, and quantum mechanics. A graduate text. Oh, this is a great book. Nelcon, MSc, Mechanics and Properties of Matter. Dynamics, statics, hydrostatics, surface tension, elasticity, friction in solids, viscosity, osmosis, and diffusion. Heinemann. And this is Nelcon. Oh, this is Heinemann Press, I see. But this is by the author. The author also wrote Light and Sound and Modern Electricity, Graded Exercises in Physics, Test Papers in Physics, Elementary Physics, Exercises in Practical Physics, Introduction to the Mathematics of Physics, with Heinemann Press and Blackie and Sons and Arnold. 1956. Addison, Wesley, and Springer Verlag have printed these books like Theoretical Physics, Mechanics, Constant, the Principles of Physics Theories, or Constant is the name of the author. Theoretical Physics, Mechanics. This is Chawla on composite materials. So this is a book from materials and like synthetic and composite materials. Fibers. Various fiberglass and carbon fiber technologies and materials. Graduate text in physics, vector analysis, velocity and acceleration, Newton's laws, linear motion of a particle, center of mass of a group of particles, angular momentum and angular velocity, Hamilton's equations, elastic media. So standard text, usually this would sit in the linear curriculum. Here's Charles Nash on relativistic quantum fields. Then the other book I have by this guy is, I believe, is about the pseudo differentiation. No, that's a great high-level account of applying that to the operator calculus. These matters of measure theory. Quantum Mechanics and Path Integrals by Feynman and Hibbs, Hibbs. So this emended edition would be per an account. Here's was read kind of from Swanson's Feynman's path integrals, or Schwinger's, Schwinger and Tominaga and Schwinger's path integrals. The effective potential, and then getting into some examples that boggle the mind, like slow electrons in a polar crystal. And then characteristic functions is like a way to pick one of those and say it's so. A bibliography. Here's something. It's like Feynman's hunch was wrong. In fact, other consistent interpretations are possible. One such alternative is the de Broglie-Bohm formulation described in Bohm and Hiley, Hiley, The Undivided Universe, an Ontological Interpretation of Quantum Theory, 1933. So Feynman and Hibbs and Bohm and Hiley, Hiley. And Duffy, Solar Engineering of Thermal Processes. Basically, how to make what you would say is be water heaters, solar water heaters. Theoretical Physics by Constant again. Mechanicals of Particles, Ridges and Elastics, Fluid and Field Flow. And that's what we'll be looking at today. Hey, have a great day, gentle readers. Good luck. Times of this world, keep in mind that you're an individual and as of the infinite integers. Reading Foundations every day.